Meeting is being live streamed. Can we start? Okay. So first of all, I'd like to thank Professor Momtchilo Russo for accepting our invitation. Dr. Momtchilo Russo is a full professor from the Department of Immunology from the Institute of Biomedical Science in University of São Paulo. So I think everybody here, everybody that works with immunology in Brazil knows Momtchilo. So he's gonna talk to us about an
Não.
Hello, o que aconteceu com o Diego?
Você já entrou no... Deixa no primeiro. Deixa na primeira, é o primeiro. Volta. Isso. Aí.
Acho que o professor...
O Diego sumiu. Você pode falar, Gustavo.
All right, so yeah, just complementing, just a great pleasure to have Momtchilo in our opening conference here of our course. And thanks very much, Momtchilo.
Okay, thank for everybody for the invitation. I'm happy to give this seminar, and we're gonna try to Gustavo will show and I will speak, and I hope we both can get together to be a good seminar. So I will talk about intranasal vaccine. So the first thing is we give the vaccine against SARS-CoV-2 by the intranasal route. So it means that it goes from the nasal route and goes to the lung. So it's intranasal, but reach the lung. It doesn't stay at the nasal cavity. It goes directly to the lung. This is the one way we do our experiment. But before I go to the data that and the paper that we published, let me show some historical important facts that drove us to these experiments. So first, next slide. So first, I have to acknowledge that the work was actually coordinated by Luciana Mirotti. And she was a former student, a PhD student, postdoctoral student at my lab, and then she moved to Fiocruz. And at Fiocruz, there was a project in Nova about COVID and things like that. And we applied. It was like one small test to say what we're gonna do, and we got the grant. So, and then we did an joint venture, USP and Fiocruz. And also we contacted Leda Castillo that gave the spike protein to perform the experiments with vaccine. But also we needed the help from Maria Cássia Correa, Instituto de Medicina Tropical, from the medical school of USP, and her team, and also an BSL lab where we can do the experiment with the virus. So it was, and this was done by Mario Irata. So this is the whole team, and then we have a lot of people from each team. From my team, from Luciana, from Leda, just her, from Cássia, 5 people, and from Mario Irata, one person, Livia Dati. Okay, a postdoc. Next one. So this is to show that let me. Well, we talk about vaccine. So the first vaccine was done with cholera vaccine by Pasteur. So the Pasteur is very important, Louis Pasteur, in vaccine development. And how was done this? Next one. This was done. So somebody left an age and bacterial culture and went to vacation. And then this bacterial culture aged. And when he came back from vacation from the lab of Pasteur, he injected the chicken with cholera. And, and what happened? The chicken did not develop a disease. And if he injected a down you can see, if injected a fresh bacterial culture, the chicken will die. So something happened with the agent that did not kill anymore the chicken. And then this that was injected with the agent bacteria now received a fresh bacterial culture, and the chicken was alive and didn't. So then you have one vaccine against cholera, and this was important for the people working with chicken, and this is an important economical problem. So Pasteur always was very good to help people in with chicken or with wine and so on, fermentation and so on. The next one. Uh, and another important finding in the vaccinology, let's say like that, was that the vaccine could be transferred by serum. So then you have at left one guinea pig that received serum from an exposed animal, and then she get diphtheria. But if she uh, receive a serum from an animal that received sublethal dose of toxin and then is injected with diphtheria bacteria, no diphtheria. And of course, this is specific because a bacteria of strain B did not induce protection. So this was a major advancement, and it's called humoral passive immunity or antibody-mediated immunity. Next one. So when they found that you can take, like say, proteins and immunize the animals, they started to do all kind of vaccine against everything. And they have this experiment they did at Monaco with this crusader. I don't know how it's in English, and this ship, and they wanted to make like next one. They wanted to next. Yes, okay. Back. I'm sorry, back because that's exactly. They wanted to immunize a dog against the venom of jellyfish that you say Physalia. It's a fragata portuguesa. So it's a kind of agua viva coelenterate that has a poison. It's a complex mixture of polypeptides and has a lot of toxic effect. So they wanted to immunize a dog. Next one. And what they found, no? So these are people important. Charles Robert Richer and Portier. So Richer and Portier, they got the Nobel Prize by the term coined as anaphylaxis. It means you have a dog that following repeated injection of jellyfish toxin, which was tolerated well on the first administration, prompted the first inside. So instead of protecting the dog died. So the origin was a Greek that means opposite to prophylaxis. It's without prophylaxis, so anaphylaxis. And these are occurring specifically after one or more than one dose. And the response it's always a prerequisite after the first exposure. So this is an hypersensitivity reaction. Okay, so and this is an important concept in immunology. So you have immunity, but you can have hypersensitivity. So the immune system is friendly, but also it might be very dangerous. Okay, next one. Next one. So I will show now the story to show how the immune system is good and bad. Okay, so Robert Koch discovered Mycobacterial tuberculosis that causes tuberculosis. No? It was very important. He was from the school, the German school of medicine, and he also is important with other people from Germany on vaccine development. Pasteur is one school, the German school, France and German. Next one. So what he discovered? He discovered a lot of bacillus, anthracis, mycobacteria, Vibrio cholera, and then he discovered tuberculin, and he got the Nobel Prize. And this is the day that his wife was going with him to get the Nobel laureate. And in the right side, you have the Koch in a horse, and then you have a serpent. And they say that he wanted to do a vaccine against tuberculosis, and he failed. So it was a big failure. No? He didn't know why. He could have done it, but he couldn't. So they had a problem. What was the problem? Next one that he faced. So I will show this problem. He faced the hypersensitivity, but now it's not the immediate phase, but it's the late type hypersensitivity to protein. And here it's shown that when you inject tuberculin, which is a complex of protein, or even if you purify the protein from tuberculin, then you're going to have an delayed type hypersensitivity that is schematically shown in the next slide. The next. So if you look in the upper figure, then you see perivascular infiltrate, these blue spots around vessels. And then if you look, what are these perivascular? It's full of mononuclear cells. And in the left side, you see that at 4 hours, there is a little inflammation, and at 48 hours, you have a strong. So this is a delayed type hypersensitivity. It's not like anaphylaxis that it's immediate. Okay, next one. Now, and what happened was exactly this with Koch. So he injected, and he have next one. He have an exaggerated back. He exaggerated delayed type hypersensitivity, and this you see it's a necrosis, and a lot of patients with tuberculosis developed these lesions. Some of them probably died, and this was the problem of Koch. Okay, at the time when he wanted to make a vaccine again. So you might want to make a vaccine, but you can make hypersensitivity. Next one. So to conclude of this next, we can say, put another one, another click. Well, maybe it's not. Okay. Do you have the immune system? No? And then you can have hypersensitivity or immunity. You can have inflammation or intolerance. And this is how the immune system plays. you might have a lot of hypersensitivity, very little immunity, or a lot of immunity, very little hypersensitivity, very little inflammation, or a lot of tolerance. And this is how the immune system works. Okay. Now, this to say that the immune system is good and bad. Next. So I had my former advisor is Mario Mariano. Well, in memory of Mario Mariano. And one day he said, do we need adjuvant to induce delayed type hypersensitivity? Why he asked this? Because he worked with mycobacteria that Koch worked. And then you have the classical hypersensitivity when you have BCG or mycobacteria. Anytime. Then you have the light type, and you wanted to do an hypersensitivity without bacteria. Okay, the adjuvant means bacteria. I will go back to this next one. So what he did was he took an egg, then he boiled the egg, then fixed the egg in ethanol, then hydrated in PBS, and then he put the egg implant, this egg implant, egg white implant, in the subcutaneous tissue. So, and then he left this for 3 to 4 weeks. What was the rationale? He said, well, the mice will get inflamed by this implant, and this will make a chronic inflammation. And then he will react to an protein derived from hen egg, okay, of albumin. Okay, so next one. So he injected the ova in the foot pad, which is the way to study inflammation. And what he found was that. Next. So he found and he showed me, you see, Momtchilo, we have delayed type hypersensitivity at 24 hours. And then I asked him, what about this in the beginning? What are these peaks? How do you explain them? He said, I have no explanation. Oh. And then I said, and why it's 24 and not 48? He said, I don't know. So we said, okay, let's see histology. What happened in the foot pad? Next one. And when he cut it in foot pad, what we found in this, if people can see the cells, you can see these donut-shaped cells, right? That are eosinophils. So instead of mononuclear cells, he had a lot of eosinophils. And then we found out that the egg white implant was inducing an eosinophilic reaction, which we have here, a late phase of immediate hypersensitivity. So if we look at the graph, he had an immediate hypersensitivity followed by a late phase. Exactly what happened with people with asthma. Okay, so the asthmatic get the allergen. Oh, back. Okay, the asthmatic get the allergen, and then he had a problem. This resolve, but then after 4, 6, or 24 hours, it gets worse because now he has an infiltration of cell. It's next one. So the two phases of the asthmatic response. First one is with IgE and mast cell, when you have liberation of mediator. And the second late phase between 4 and 24 hours is the infiltration of T cells, eosinophils, and mononuclear cells. Next one. So to resume this, next, early phase and late phase. Then you have the early anaphylaxis, cellular infiltration in the late phase. So next one. We then sent to Journal of Allergy. This was a long time. Since then, I am working with lung in 1997. And on the basis of the model, we proposed suitable model of asthma. Next one. So this was published. Ana Lúcia Pereira was the first author, and Sônia Giancarlo was the advisor, and then Momtchilo, Ana Angélica, and Mário Maene collaborators. Okay, next one. So now it's in Portuguese, but I wrote this during the pandemic, no, and because there was a strong anti-vaccine movement, and then I said, you have to be vaccinated against everything, but I'm just giving two more information about vaccinology. First is Gaston Ramon, is from the Pasteur Institute. And the second one, it's an English, that is Glennie, Alexander Thomas Glennie. So Ramon found out that when he had a good serum, antitoxin serum in horses, no, when the horses had an strong inflammatory reaction at the site of injection. So in order to make better serum, he started to make inflammation at the local where the toxoid was injected. And he coined this as adjuvant from adjuvare, help to help. No, exactly this. So, and the next one, no, next, Glennie and co-workers were first to demonstrate that compounds that have aluminium, they are good adjuvants. So they use the toxoid from diphtheria, let's say, or tetanus, and they were precipitated by a salt of aluminium, a double salt, aluminium potassium sulfate salt. And he found that the response by this precipitated alum increased the immune response against toxoid. This is the second part of this I published in Journal of USP in 220. Okay. Next one. So just to make clear, because everybody say alum, aluminium content are referred as alum. But next, but alum, actually, alum, okay, go ahead. Go ahead. Thank you. Alum is exactly this. It's alum, it's a potassium aluminum sulfate. It's a double salt. This is the alum, the real alum. But now everything that has aluminium, it's considered alum. Next one. It's wrong, but it's okay. Aluminum hydroxide gel is the most, next one, adjuvant used nowadays. Excuse me. So this is what we use, aluminum hydroxide. It's called alum, but it's an hydroxide, gel of hydroxide, aluminum. Plus, next. So, and this was done by another Nobel laureate, von Behring, from the German school, with Kitasato, that helped him, and he worked a lot with vaccine and things on. Kitasato from Japan went to Germany to work with von Behring. Next one. So now I have a timeline about, because this was the first vaccines used in humans. So I just we're going to call some attention of what is alum. Next one. Okay, in New York City, just a minute. In New York City, they did diphtheria vaccination, and they reduced in 99% the mortality in 1910. Okay, in 1989, now we know a lot about immunology. They found out that alum is a Th2 type adjuvant. So it's not Th1, it's a Th2 adjuvant, okay? And of course, Alexandre Glenny was elected for the Royal Society, and it was very important gold medal award also. Okay, and lately they started to study what alum does. Next one. And now I will talk about the ALVA model just to start to talk about adjuvants. Then I will go to the main subject of what I have to speak today. So if I use one model which we use it two sensitization with alum at day 0 and 7, and 2 intranasal OVA challenge. So this is the OVA model of allergy, of respiratory allergy or allergic airway disease. Next one. And why this? There are a lot of reasons. Next one. But I will not give a lot of reasons. Just say that after 24 hours, the second of a challenge, we have everything we want to measure. We have cells, we have cytokines, and we have IgE in the bowel. And also we can measure in the serum if you want cytokines and antibody anti-OVA. So this is a good model because after the second OVA challenge, everything is synchronized. Cells, antibodies, and so on. So you don't have to, if you want cell 3 days, if you want cytokine 24 hours, you can do everything 24 hours after the second challenge because you have mobilization of memory T cell to the lung during the first challenge. Next one. So, and then if you look, next one, if you look this is, it's a bronchi and a vascular, and then you have peribronchovascular infiltrate of eosinophil. If you cannot see, it's not, but there is a lot of eosinophils in this, and then you can look cytokines, measure cytokine IgG1 and Ig. Next one. So I use this aluminum model, and then we asked, aluminum salt gel are TLR independent adjuvant and have been boosted to boost antibody response, have been used to boost in alum-based vaccine, such as these are the first vaccine, diphtheria, pertussis, and tetanus toxoid. Everybody get this triple vaccine. Next one. So we asked, it's possible to modify alum adjuvant Th2 activity with Th1 type adjuvant. So if we mixture something that's Th2 with Th1, what's gonna happen? Next one. So we have here one. This is a lot of paper that we publish, but I summarize them in this table. So if you have alum with alum, you have a Th2 response. If you have OVA with low dose of alum, then with low dose of LPS plus alum, so I introduced Th1 adjuvant or high dose, what we see in the lung, we have no inflammation. So it blocked the inflammation. It blocked the inflammation. However, if we give the intranasal sensitization into alone, you have tolerance. You see the difference. If you give subcutaneous, no tolerance. If you give intranasal, you have tolerance. If you give with low dose of LPS, you have the Th2, Th17 response. If you give a high dose, you have Th1, Th17 response. So this is the whole thing with the OVA. So OVA, it's a very good model to study immunology. And I was by Luciana worked with OVA. A lot of people in my lab worked with OVA. And we, of course, are based on this experiment. Next one. So Luciano, this did work. He gave OVA and then used TLR2, TLR3, TLR4, TLR7, and TLR9, and during sensitization, and then giving 2 OVA challenge, and then she looked at the inflammation. I summarized this. Next one. So naive, you don't have inflammation. OVA in the right upper, so you have a lot of inflammation and mucus formation. Then you you have TLR2, TLR4, TLR3, TLR4, TLR7, and TLR9. If you look all of them, TLR4 and TLR9 are the best one to dampen allergic inflammation. Next one. So here it's the summary. So I just believe me, TLR4 and TLR9 agonists are the best one to do. Of course, the TLR9 CpG is better than TLR4. Okay, a little bit better. It's more efficient to dampen allergic inflammation. So we choose the TLR9 to use. Next one. And here, it's again a lot of experiment, just a summary of what we understand about OVA. So OVA, you have allergic inflammation, in the bowel, a lot of eosinophils, and then you have high Ig and low IgG 2A or 2C. Okay, if you mix OVA with CpG, then you have no inflammation in the lung. You have low Ig and high IgG2C. The IgG1 is similar. Okay. If you now go to MID deficient mice and you do the CpG, there is no action. So all this parent, the MID pathway is important for CpG-mediated anti-allergic effect in the alum of alum. Yeah. Then we went a little bit further and we studied IL-10 knockout mice. In IL-10 knockout mice, if you put CpG instead of Th1 cell or nothing, you have a Th1 inflammation with a lot of neutrophils and low Ig and high IgG with a lot of Th1 interferon gamma cells. And finally, if we use IL-10 knockout with IL-12 knockout, instead of Th1, you have Th17 response. So you have you can have the Th2, Th1, Th17 inflammation just mixing with this. Okay. Also, this is what we knew. Okay. Next one. So now we can talk about viruses. So sorry for all this introduction, but I think this is important to go further in the research. So this was our background to apply for the research. So how viruses are recognized? Next one. Now, if we look this table here, it's very complicated microbiology. So you have a lot of type of virus, and it's very difficult to understand. But for immunologists, it's not so difficult. Just look that viruses either have DNA or RNA, and this the immune system know how to recognize. So for the immune system, doesn't matter if it's a RNA, DNA, or no, it just want to know it's RNA or DNA. Next one. So how we recognize RNA or DNA? Of course, you can recognize the virus like here you have porine, hemagglutinin, F protein, envelope, but these are TLR2. But inside, either you recognize by DNA, by TLR9, or by RNA, TLR7 and 8, or by double standard RNA, which is the TLR3. So you have this endosomal toll-like receptor that recognize viruses. And with this, they recognize all viruses, all. So this is a simplification in recognition. Next one. So just to show here, we published this work on asthma and TLR and so on. But then you see in the endosome TLR9, 7 and 8 for RNA and TLR3 for double standard RNA. It's a little bit different, but at the end, everything is similar. Next one. So another way to recognize viruses is by helicases. So if they are in the endosome, then it's TLR3 and the other 7, 8, and 9. But when they are in the cytosol, they are recognized by helicase. That here we have two examples, MGA5 and RIGI. And then what they induce interferons, and interferon is the most important cytokine for viruses to block the replication of virus. And then you have cytokines that will make the inflammation that you have when you have virus infection. Next one. So here I just summarized this how an infected cell can recognize. If they have RNA or DNA, then you have TLR7, 8, 9. If it double standard, and if this leaks, if you have leakage of this RNA or DNA to the cytosol, then you have the helicases that might also by the mitochondria signaling, and they will produce interferon alpha or interferon beta that are antiviral substance. Next one. Okay. And then just to finish with this recognition, you still have another sensor that is stimulator of interferon genes that distinct. And distinct also recognized by a cyclic GMP synthase. He recognized this cyclic GMP and then goes signal to the Golgi, and then you have the production of interferon type cell. So STING is another. I think I finished with this. So STING, but basically TLR, STING, helicase, and STING. Next one. So let's go back to vaccines. So the vaccine started, if you look here, with exactly with alum. So alum has more than 100 years of usage. No, so you start to use alum, and then slowly by slowly they started to add things to the alum or developing other types of adjuvant. So we are now in a new era of adjuvants. So we now know a lot of immunology. And now, so if you look, the CPG was introduced in 220, you know, and these CPGs use it in humans. But you have adjuvant systems, and you have squalene, and you have a lot of things to understand. But they always put DNA recombinant in the vaccine also. So, excuse me. Next one. So here, what type of vaccines we have against SARS? So we can use recombinant vaccines that we use it. We use it, the spike protein. No, we can use inactivated vaccine, viral vectors, attenuated vaccine, DNA DNA vaccine I might comment from chimpanzee or human, no, adenovirus, virus-like particles, and RNA vaccines that are much that from Pfizer. Okay, and what is the goal? At least the goal of vaccine is to produce neutralizing antibody. This is important because if you block the infection with neutralizing, that's not always very simple. It's okay, you are there. You might now induce memory B cells, and then you might want to lyse or inhibit the growth of the virus in the cell. Okay, this is the cellular immunity. Next one. So if we go here, then you have cytotoxicity cell that kill the infected cell, or B cells that are neutralizing the antibodies. Next one. But when we look, what are cytotoxicity cells? Everybody will say CD8 cell. It's not completely correct. Next one. You have cytotoxicity cell that might be CD4 or might be CD8. So, and both produce interferon gamma that is against the replication of the virus. So you cannot say, no, CD8 cell or no, all of them are important. Okay, next one. And here, just to say that CD8 cell, CD8, CD4 cell are cytotoxic by different mechanisms, Fas ligand, and so on. Of course, Gustavo can talk about that much more than I. Okay, besides the cytotoxic cells, cytotoxic granules. Next one. So we used the murine model of infection. I'm going to the SARS-CoV-2. It's called K18 human hACE2. K18, it's a keratin promoter, 18, no. And then they put this K18 in mice, and then they transfected the human hACE2 receptor, that is the receptor for SARS-CoV-2. So this is a transgenic mice. Okay, it's a good model. It's the model, I would say, that is for the mice is the worst because they all die of infection. So it's completely, it's just, you infect the mice, you're gonna kill, or you're gonna lose a lot of, of weight. If you use other type of, like guinea pig, they get the virus, but they recover. So you have different ones. And this one is little. It's very little for the mice. And then you have bilateral pulmonary infection. Of course, depends of the viral load you put, but 10 to 5 virus kill all of them, 100%. So we use this model, and it's short. It's just 7 days we study. Next one. So what we use it as formulation? We use it a formulation, a cationic liposome that we learned with Karina when she was postdoc in my lab, and she used it for other reasons. But we use the same DOTAP, we call cationic DOTAP. It's a cationic liposome. And then we put the chimeric spike protein inside the DOTAP, and we added CPG. The CPG we used, next one. The CPG we used, guanisine, and cytidine, oligonucleotides. They are synthesized, and you have different types. We use, if somebody wants to understand a little, we use the type C. The reason, it's because work in human and in mice. So we choose the one that work in human, in mice. Next one. And then the first thing we did was to study dynamic light scattering. What does it mean? I didn't know nothing about that, but I learned. It gives you the size. So if you look here in G, the first one is liposome. So the size is by, let's say, 100 nanograms. When we put the protein S, it goes to microgram, 1.5 microgram. It's not anymore nanogram. So if you go more than 1,000 nanogram, you are getting microgram. So even it's nanoparticle or microparticle. This is microparticle. But when we put liposome and CPG, doesn't change too much. But when you mix CPG, protein S, and liposome, then you get around 500 nanogram, a little bit less than 500. No? And then if you look for in the right side of the slide in E, you look the potential of the formulation. Then the first one, the liposome, is positive. Of course, it's cationic liposome, so it's positive. Then when you put CPG, the protein S, the protein S is less positive because protein S is negative. Ovalbumin also is negative. And then if you put liposome plus CPG, you get much more negative. And when you mixed protein S CPG, you get negative, but a little more less than only CPG. So this is the formulation is cationic liposome, and protein S and CPG. Next one. So what we had, what was the hypothesis? The hypothesis that we sent when we wanted to innovate in Fiocruz was saying, okay, non-vaccinated. So what happened with people that are non-vaccinated? When they are infected, they start to initiate the immune response. So it's a race. If you can do a good immune response, you're going to survive. But if you do the wrong one, you die. And this happens with people, okay? So some people die. It's not all of them, some of them, and depends, of course, of the amount of virus that you get, the virus load. If you get a lot, it's worse, okay? Well, the vaccine that are used in the, that have been used, all over, are vaccines that are intramuscular. There is reason to be intramuscular, but if somebody me ask, I will reply after. No, and what happened with this? So you need to recruit, you boost, you sensitize the the person or the animal, and then you have to recruit these cells from the lymph nodes that are there to the lung. So you have a delayed response. You need the recruitment of effector and memory T in this cell, and then you have a delayed lung response. And finally, why we give actually intranasal, but as I told you, go to the lung because you have the wall response in the lung, first in the lung. So then you have memory cells in the lung. You prime the lung for the infection. This was the working hypothesis. Okay, so you prime the mucosa, no, and then we use next one TLR9 CpG. This I already commented a lot. Next one. And of course, I showed this slide. So it's in the some next one. And what we did first was to study what is the difference between intranasal versus subcutaneous vaccination. No? So we give our vaccine intranasally or subcutaneous. Next. And what we found is both. You can see, okay? So you have three groups: non-vaccinated, and we infected with Wuhan strain 10 to the 5, okay? At day 21, okay? We can do 14 or 25. And the most of our experiment, 0.7 vaccination, 21 making the experiment. And then if you look the days post-infection, for survival, you see that non-vaccinated, all of them died by 7 days, and none of the vaccinated groups. No. It means that subcutaneous or intranasal, in terms of mortality, are equally good. Okay, and then if you look for the weight loss, is the same. The animals start to lose weight loss at 4 days. So around 4 days. And in 7 days, you have to finish because they lose more than 20% of the weight. You have to sacrifice them. Okay. And the others don't lose. Okay. Okay. So the first thing was, wow, the vaccine, both are very good. Next. So we wanted to see the clearance in the lung and in the nervous system. Okay, next one. And if you look the viral at day two, there is no much difference between the groups. But at day 4, the intranasal group showed lower viral load than the subcutaneous. And if we go to the brain, in the olfactory bulb, it's interesting. Everybody is positive, but in the hippocampus, which is a little bit farther, so it's paired by intranasal and subcutaneous. So they are good to prevent the infection in the brain. Next one. So we wanted to see about neutralizing antibody. What about this? Next one. And we use the plaque reduction. So if we look for antibody again, let's put the next one. Okay. Oh, no, come back. Okay, let's see. If you look serum antibodies at day 2, the intranasal has already neutralized antibody, and at day 4, much more. So, but at day 4, the subcutaneous is also it's increasing. Okay, while the control has no antibody at all. And if we look for anti IgA, that is the antibody that is produced in the mucosa and in the serum, but the intranasal induce much more IgA in the serum than the subcutaneous. Okay, if you look for IgG1, is similar. So the intranasal produce more IgA in the serum, and of course in the bowel, I'm gonna show later, and more neutralizing antibody because the IgA antibody is neutralizing also. Okay, next one. So we asked, what about the variants of concern? So we used 2 variants, 3, but I'm gonna show 2. Next one. And so we used the gamma and delta variant. As you see, the intranasal vaccination control in both. So it control the gamma and delta infection. It means that the vaccine we use, the intranasal vaccine, is somehow, it's not only based on antibody. So we didn't measure cellular immunity, but probably this is due to cellular immunity also, as suggested by the work of Ricardo Gazzinelli and the vaccine that do not induce neutralizing antibody, but protects. So we don't know what's the protect, but it protects again. We use the oh, I forgot. Okay, let's go again. Next one. Omicron. We use the Omicron. Omicron does not do anything in the model. The mice just don't lose weight, don't lose nothing. But then we look for the virus, and the virus clearance is better with the vaccine. So it's not shown here, but it's shown in the paper. Then we said, okay, let's study the intramuscular AstraZeneca and our nasal vaccine, if they are good. So we did the same thing, no? Intranasal, intramuscular, and we look. Next one. And again, both vaccines, the AstraZeneca or intranasal, protected the animals. Both vaccines, no? Viral load. Both vaccines decrease the viral load. Of course, you have less in the intranasal, but the AstraZeneca also decreases, so it's significantly. But the intranasal seems to decrease more the viral load in the lung. And then, if you look serum neutralizing antibody, they are equal. AstraZeneca and intranasal are similar serum. Then, if you look IgA, the IgA is higher with the intranasal than the AstraZeneca. And then bowel neutralizing antibodies is higher. You see, the AstraZeneca does not have, and the intranasal has. And then bowel anti-IgA antibody is higher in the intranasal. Okay, so next one. So this is to call attention. So intranasal, okay. Then we say, well, everybody was already vaccinated. Can we give intranasal vaccine after they have been vaccinated? So we did to see heterologous immunity. Next one. So we used the AstraZeneca that received 3 times at day 0, 7, and 14. And the other received AstraZeneca at day 0 and 7, and then intranasal, go back, intranasal vaccine. Of course, we knew that they are protected, and they were protected by AstraZeneca or by AstraZeneca intranasal. However, if we look for the viral load, the viral load is much more at day 2. The viral load is much lower with the intranasal boost than with the homologous boost. So it means that you have less virus in the lung. Means that probably you protect the other people from getting it. Next one. So the features, let's finalize. It's easy to manufacture worldwide. We didn't see side effects in animal models. The nasal application is less invasive and protects again needle phobia. That it's one problem. Induce neutralizing antibodies in the lung and in the blood. And of course, we looking for low cost to see if somebody want to buy our vaccine. So it's $10 a dose. And this is okay, you can go. I think I am running. And this is the paper that we published in vaccine. Somebody want to see, it's there. Okay, I will be happy to take questions from the audience.
All right. Thank you very much, Momtchilo. Let me stop sharing here. We open for questions first from the students.
Okay.
All right. So whoever wants to talk, just open the mic and ask questions, or if you prefer to raise hands, there is a reaction button. Come on.
Bruno.
Bruno, all right. Just warm up, but we expect the questions from the students. All right, Bruno, go ahead.
All right, thank you, Gustavo. It's just to give the students time to formulate their own questions. So let's start with one. First, thank you, Dr. Momtchilo. It was a very exciting talk, very interesting. And you described an amazing body of results on how exposure to different adjuvants, alone or in combination, define the subsequent adaptive response and the type of response elicited by re-exposure to the antigen. But I was wondering if you could elaborate a little bit more on what is going on with the APC cells. It's just a matter of different differentiation activation profiles, are different types of APC cells involved in the different sites and adjuvant combination, or is there an engagement of different cells in the microenvironment as well? Thank you.
Okay, it's an excellent question. So when it's excellent question, I say, well, I don't know to answer, but anyway, you have to study. I didn't study if you look my work, I'm going to the end. I'm not in the beginning. I sensitize and then challenge and then look what happens. So all my work was done at the effector phase, not in the induction phase, where you can, what type of APC are doing. And then this is fascinating work. I like a lot dendritic cell, but I have no idea of what is going on. But I can say that they are now because the vaccine that came from Pfizer, they use nanoparticles also. They use lipids nanoparticles, and they because they wanted to protect the RNA because you're gonna have RNAs. So they no, let's inject in the muscle, but we're gonna protect. And what they found, and this is a lot of some. One of them was published in Immunity that these nanoparticles they induce very strong follicles, germinal center formation. So they somehow they are doing something, and and uh, and I they of course they studied they and the work that I read was they said that ionizable liposomes are important. If they are not ionizable, they are not important. My cationic liposome, it's not ionizable. So so they should study my also to see what's going on. It's a new, I mean, nanoparticles are new adjuvants, and it's a new. Now you everybody. We are going to study now. The first we wanted to see protect or non protect, and so and the first experiment we did, it's protection, 100 protect. So it's fantastic. And we took a lot. We wanted to make a patent, and still we don't have a patent. And then we published this without patent and so on. But it took a lot of time. But this is another thing because we wanted to offer the vaccine to Butantan and so on, but didn't go further. So, but your question is important. So, what the dendritic cell sense, and then you have human in mice, and you probably it's different. So you still you have to do experimenting non-primate humans to understand whether it's similar to mice or not. And there is a lot of different things to study. But I I don't have the I don't understand even. If you ask me, I don't know. Sincerely, I don't know what is going on. I know that the factor phase is like that. You have antibodies and so on. We started to study the germinal center formation, but I didn't finish. What I know, that's for sure. The IgA business is really fantastic. And then uh, uh, but even when you want to study the IgA production in the lung, you get a little bit um, lost because there is very little. The IgA, it's very well studied in the gastrointestinal tract, but not in the lung. And now it's incredible for how they come and so on. We're gonna study that, but not dendritic cell.
Okay. Thank you very much. But I'm sorry that I brought up a question that you did not have a ready answer yet, but we can look into it. But at least we gave some time for the students to start asking their questions, and we have a question from Lucas Bolini, that is a student here at the Biophysics Institute.
Hi, Momtchilo. Thank you for your talk. It was very, very interesting, and it was also very nice to see this historical introduction on vaccines. It's always a good reminder. Regarding what you were talking about right now with Bruno, I was wondering if you know or whether you have checked whether this IgA production is because of lymph node adjacent memory B cells, or whether you have plasma cell differentiation and migration to the bone marrow, and thus whether this IgA production is long-term, and whether this is associated with long-term protection against infection, or whether this is just like a short-term, immediate, like first week's protection, and then this disappears in the long term. Yeah, I guess basically it's just, is this model associated with long-term protection against infection?
Oh, okay, that's, I mean, this is open. It's an open question. And you are, oh, thank you for commenting about the history. And first of all, I am professor, so I like the immunological story. So I like, and it took a lot of time. I couldn't go directly to the vaccine and discuss a lot of things, even discuss the IgA problem. So, and who is, well, I mean, then when you go to the IgA problem, when you go to humans, it's different from mice. The human have some channels that produce the IgA, and the mice has no this. So it's different mice and human. And where is produced? I think that's produced in the mediastinal lymph nodes. I don't see in the lung that a lot of people say that is lymphoid associated mucosal tissue. I don't see this. It could be if it's chronic, it might have mucosal associated lymphoid tissue, mouth. No? Well, I don't see. I don't think it's mouth. I think that they are produced, and they are produced outside, and then they are transported. And this is known by polymer. It has to be a dimeric IgA. They have to have the J chain, and then the polymeric IgG receptor make the transcytosis and go to the bowel. This is for sure. This is and then I find out not only IgA go to you, the IgE also go. No, and I think IgG also. We started to study this, but they are transported. We can study this in more detail. You can knock out the transporter, and they will not go to the IgA will not go to the ball and to see what happened. But then you have to do the knockout in the transgenic, and it's time consuming and so on. So that's what was your question, the IgA, right?
Yeah.
But for sure, sorry, but IgA is neutralized. That's for sure.
Yeah, the second part was just whether you think if there is a differentiation to plasma cells and migration to the bone marrow. It's just a...
I haven't looked at the bone marrow. I haven't looked. I think that the sensitization reflects in the bone marrow, but I have not. I even think that T cells go to the bone marrow.
Mhm.
J T cells.
Okay,
But
thank you. Thank you very much.
Okay, I think Bartira had a question and a problem with the mic. Do you still have it? No, now you. Can you ask Bartira? Hello, how are you?
I think we will need to read.
No, we are not hearing you. Right, so can I ask your question that you put in the chat, Bartira? All right, so Bartira, first of all, congratulate you, Momtchilo, for your excellent talk. And she asked whether you have tried to vaccinate mice intranasally with the AstraZeneca vaccine.
no, I didn't do that. I didn't do that. I just did with the AstraZeneca because the AstraZeneca was the vaccine from Fiocruz. So we took the vaccine, they give intramuscularly. So we wanted to study this. No, I don't know what's gonna happen with the intranasal. I know some papers that say that intranasal sometimes is toxic. No, and they said that the Pfizer could, but there are other papers showing that no, it's not our paper, it's not the first one. There are other papers showing that intranasal works
So,
well.
Momtchilo, she's curious about the use of other vaccines intranasally. If you are aware of anybody that has used it.
Yeah, if she go to the literature, even in SARS-CoV-2, in mice, there are, I think, two or three papers with the intranasal vaccine, and it's always the same result. It's better than the others because it's mucosal immunity and so on. So it's a little bit what we when we applied the Innova, we said, well, Sabin gave the oral vaccine and IgA, and based on this, we want to give a nasal vaccine and IgA. This was and they granted. Was just a few words, and this was granted immediately. So the idea was good. I mean, and the arguments, of course, were good. And I think that this will not the nasal vaccine. It's important for infection, respiratory infection. Why not give this in the respiratory infection? Maybe not for others. For instance, dengue. You don't need it. It's different. So then you use a different approach. But I think for influenza and other respiratory disease, I think it's important. And what she asked? Let me make a comment. The adenovirus vaccine, I don't know if you can give it more. How many times you can give it? Because you're gonna make an immune response to the vaccine because it's adenovirus virus, and then you're gonna reject it. I don't think it's a good it's a good strategy, in my opinion. So I'm not selling my vaccine. The vaccine that you have a liposome, and then you put something that resembles a virus, that's oligonucleotides, and then you put the protein that you want to target. I think then we can use it for all type of virus. If this works, you have to try. But if this works, so But if you give adenovirus, then what happened? The adenovirus will induce an anti-adenovirus immunity. So the mRNA is better for components of the vaccine.
Momtchilo, we are running out of time. I will let Julio ask a question, but before that, just a quick question for you in terms of the experimental model. One thing about this nasal vaccine, hypothetically, is that it would be important to prevent the transmission of the disease. So you talk a lot about protection, but we haven't talked about the transmission of the disease, which is not really prevented by the available vaccines. So have you, or is it possible, or have you did some experimental work with the transmission in mice? Can you infected one mice, put it in a cage, and check for transmission?
Yeah, that was a question. We did this question. Luciana wanted to do that, and I said this will not work because the mice first they don't transmit by droplets, so they have to get in contact. So and it's not easy. People do that, but some of them did, but we didn't do. And I was one of the say, you're gonna lose your time because you're gonna have a lot of mice in the cage, and then you have to know who is infected, or either they die or lose, and then you take them out. It's not very simple to study that, but when you do the viral load in the lung, if you have less virus, of course, less transmissibility. This is for sure. Yeah, but I mean, this is very logical. But we didn't do that.
That's good. That's good enough. Okay, Julio, quick question, quick answer.
Yeah, Momtchilo, amazing. It's a lot of work, a lot of work. Working on NB3 must be crazy. This is in connection to what Gustavo has asked. You mentioned that the Omicron experiment, the IgA is not relevant, right? Because you don't, I mean, it's not lethal, okay, but when you look at viral load, you can deduce that IgA is not being important. So you have more likely a cellular mechanism involved, right? This is what we think.
I don't know. I don't agree. We didn't look for that.
Because the IgA, if the IgA is not neutralizing Omicron, and you have a reduction on the viral load, you have something else working.
Okay.
And that's what I'm saying. So so there is a component in your model that is heavily dependent on a very good cellular immunity. So it's probably the situation that we are facing now. We are all immunized. We get, the infection a little bit, some mild infection. It's okay. So it seems in some way, maybe it's answering Gustavo's question, because it is unlikely that a mechanism that is cellular based would actually help to avoid transmission. Do you agree with me?
As usual.
What do you mean?
No, we are a long time. No, anyway, but
no, it's an open debate. We are not talking to a company. We're just.
I think that IgA is neutralizing the virus in the lung.
Okay? The Omicron? No, but the Omicron experiment shows that there is something else, right?
let me talk about them.
Okay.
The Omicron, you know, what we, this is not what happens. I work with people, physicians in infectious disease, and I say Omicron does not to the mice in the model. They said, don't say that. You know? So it's something with the mice, but not with the humans that are infected.
Yeah.
In humans is different, but in mice, if you inject the Omicron, they don't lose weight and they don't die. So they don't do anything. What we look at we looked for the viral load in the lung, and then we found that it was decreased.
Right.
Why it was
Exactly.
decreased? Two reasons. One, IgA antibody blocked the entrance. The second is T cells. So I don't know. It might be that
So it's working as a neutralizing IgA. So IgA in that, yeah. So I didn't understand that point in your introduction. Okay.
it's working. And
I
then
thought that you didn't get neutralizing because you used the Wuhan
no, it's neutralized. And
against
we measured
Omicron. You
in the
neutralize Omicron.
exactly.
Uh-huh.
Neutralized Omicron.
Okay.
All right, guys. We
All
gotta
right. All right.
go.
All right.
It's in the paper.
Yeah, we gotta go.
Yeah.
Thank you, Momtchilo, very, very much. Little note for the students. I wrote down in the chat, but I haven't yet fully established the Moodle. So hold on to your reports. Normally is until the 12 noon at Wednesday. So it will be ready for them. Okay, just not now. Thank you very much for everybody that participates, asks questions. Hope to see you next Monday. All right?
Maravilha.
Okay,
Okay.
thank you guys.
Ciao.
Have a nice
Ciao.
weekend.